Now, we move to study the relation between the electric field and the electric force on a point charge. And this relation is a very important relation and a crucial relation actually, and we have to understand it thoroughly and so that we can apply it. So it is this simple relation. It says that if you have an electric field at some point and you bring a charge Q. Now this charge Q is a point charge. This is my definition, but it doesn't need to be a positive charge in this case. Okay, so there's an electric field generated by some source charge in some region in space, and you bring a positive charge, point charge Q, and put it at a given point in that electric field. Then the electric force that this will test charge, this point charge feels due to the field E, which is existing there at that point due to another source charge, will be given by this relation. The force will be equal to the charge, to the electric field at that point, multiplied by the charge. Now, this is a vector equation. The force is a vector and the electric field is a vector. And when you substitute Q in this relation, this is crucial, you have to substitute it along with its sign. So if Q is positive, then you are multiplying the electric field, this vector, by a positive scalar, so the force will be in the same direction as the electric field. Okay? So for positive charge placed an electric field, the force on that charge will be in the same direction as the force of the electric field at that point. If the charge is negative, Q is negative, then you are multiplying this vector by a negative scalar. So the result here, which is the force vector, will be opposite to the electric field vector in this case. Therefore, if we have an electric field in some region space, at some point in space, we bring in a negative charge, point charge, and put it there, then in this case, the force on that negative charge will be opposite to, or the direction of the force on that negative charge will be opposite to the direction of the already existing electric field at that point where you have put the point charge. This relation is valid only for point charges. If you have if you put an extended object, not a point charge, in an electric field, definitely it will feel a force, but the force will not be given simply by this relation. We will see later how we can find this force. Now, this is a good checkpoint about the relation between the electric field, magnitude of the electric field, and magnitude of the force. Note that it's talking about magnitudes, so you have to consider this equation taking the absolute value of both sides, because I'm asking about the magnitudes only. Now, I like to look at the electric field as actually being a tariff of the space. This just gives us an intuition about what the electric field is about. So let me just introduce this idea. Now, my idea is that you can think of the electric field created in space by some charge, some source charge, as actually being an assignment of a force tariff for all points in that space. In other words, when you bring some charge, source charge here, the space around that source charge is no more free space. It's not no more like it was before you bring it. There is something in that space. What is this something? The field. What is this field actually? When you bring in this charge, as if you are, each point in this space around this source charge will have now a force tariff. Let me elaborate on this. What do I mean by the force tariff? Well, a tariff, you know, like for example, the bus tariff, for example, when you take a bus from close to it has a tariff. So fixed value. Now, this means that every point in space will have now a value. So in the region, the space surrounding the source charge, every point in that space now will have a value for the magnitude and direction of the force per unit positive charge at that space. So in other words, it will have like a tariff, and this tariff is just E. So all the points in space now, at any point you go, you will have a tariff for that particular point telling you what will be the magnitude and direction, the magnitude of the force per unit positive charge and the direction of that force for that particular point in space. Since E is a function of space, the field varies from a point to a point, then that's tariff actually. And also if the charge, the source charge also varies with time, that tariff also can vary. Now, if you want to find the force when you place it at any point in space, just multiply the force on a charge q, whatever point charge q, whatever is this charge, you just multiply that point charge with the tariff at that particular point in space, and this is how you get the force on that particular point. So this is the idea of a tariff. I mean, you have a space, and in each space there is a label telling you if you put a charge here, then the force per unit charge will have this magnitude in this direction. So when you bring a force there, multiply it by the tariff at that particular point, and you will get the force there. So this is the idea behind the term that an electric field is actually a definition or an assignment of a force tariff for all points in space. You might like to look at it this way. This is a good checkpoint to test your understanding of the relation between the source field and the test charge, and also how to find the direction of the electric field. Now, the last thing that we'd like to talk about is the electric field, the explicit expression, to find the expression for the electric field of a point charge. Now, the starting point is Coulomb's law. Now, this is the expression for Coulomb's law. This is the force by a source charge, it's Q. Q naught is the test charge. So when you say naught here, it is the test charge. So this is the vector form of Coulomb's law for the force exerted by a source charge on a test charge that is a distance away, r, from it. Now, this r hat, as we recall from Coulomb's law expression, is a vector, a unit vector that goes from the source charge to the test charge. So this is just Coulomb's law expressed for source charge, the force between exerted by a source charge Q on a test charge Q naught. So this is the force. Now, what is the electric field? Well, the electric field is force per test charge. So you divide this expression by the test charge Q naught. And when you divide it, Q naught cancels out, and you get this expression for the electric field generated by the source charge Q at a point that's r away from that source charge and in a direction, along the direction, or and that point is a distance r along r hat, along the vector r hat, which goes from this r hat goes from the source charge now to the point where you want to calculate the field. Okay, so this is the meaning of that. Here it's quite evident that the electric field depends only on the source charge, as we have always been saying, and it is independent of the test charge. The test charge cancels out here. So the field is a property of the source charge, and it is independent of the test charge. So, and this expression is a vector expression, as you can see, and it gives you the electric field vector. Now, when you substitute here Q, you have to substitute it along with its sign. Okay, so this is valid for both positive and negative point charges. This is the electric field by a single point charge, positive or negative. Now, let's understand or look at this a bit more closely. Now, if your source charge is positive, then this whole thing, which is a scalar, is positive, and it's multiplying r hat. So your electric field generated by a positive source charge will be parallel to the vector r hat, or the unit vector r hat. Let me make this clear. This is your positive charge, source charge, and you want to find the electric field at this point P. This point P is at a distance r, this distance is r, and it is in this direction r hat. R hat is a unit vector which goes from the source charge to the point where you want to find the field. Now, this equation suggests that the expression is equal to this. You take Q, K is a positive, Q is positive, divide by r square, and the direction of the field will be along r hat. And as we have seen before, the electric field of this positive point charge at this point P is definitely pointing in this direction. So it is along r hat as we expect. Now, on the other hand, if you want to find the electric field of a negative source charge at the point P. Now, the r hat vector is still defined as pointing from the source charge towards the point where you want to find the electric field. So it is in this direction. But now, since Q is negative, this whole thing is a negative scalar multiplying r hat. So E should be anti-parallel to r hat, yani pointing in the opposite direction of r hat. And indeed, if you look here, as we have found before, the electric field of this negative charge here at this point P is in this direction, which is against the direction of r hat. So this is how you find the magnitude and direction of the electric field of a single point charge. It is given by this expression.